This is question 1F, and this is a pretty tricky looking one. It's got an op-amp and AC and a capacitor, and we haven't really seen that before in our lectures. So let's see what's going on. Okay, the question says that the op-amp is ideal and operating in its linear region. So linear region, what does that mean? Okay, what that means is that we do not have to consider the op-amp power supply voltage rails, okay? So you know how if the output of the op-amp exceeds VCC or VEE, then the output gets clipped. Well, when we say that the op-amp is operating in its linear region, it means that the op-amp just works according to its equation without any regard for getting clipped by its power supply rails. So that's what linear region means. Okay, so now what's special about this problem? Why is this asked? Why is this a twist, a challenge? What we have to do is keep in mind what the op-amp properties are and apply AC circuits to it. And so it's an extension of your knowledge of op-amps. So keep in mind the op-amp properties. So let's just make sure that we know them. Keep in mind the op-amp properties. Okay, so we know that for op-amps, no current flows into the input terminals. So in here and in here, there's zero current. Okay, so we denote that by positive input having zero input current and the negative input having zero input current. And then we know that with negative feedback, that VP is equal to Vn. So that means a virtual short if we have negative feedback, which in this case we have negative feedback. So for this question, the op-amp is working in its negative feedback configuration and Vp is equal to Vn. Okay, so now we can use nodal analysis to find an expression for V out, but let's look at this. Let's look at this 500 ohms at the output. So what's interesting about this is that it's a little bit of a trick. So this 500 ohms does nothing to affect the behavior of V out when the op-amp is ideal. So this 500 ohms does nothing to affect V out. So we can ignore it. So it is a distractor for you. Well, now let's use nodal analysis to find V out. Nodal analysis is very useful for analyzing op-amp circuits. So when we're doing nodal analysis, we denote a node, so I'm going to call this A, and I'm going to describe the currents flowing out from every branch. As you know, when we use nodal analysis, we consider it to be the highest voltage and that all currents flow out from it. Okay, so let us just say use nodal analysis to find V out and then nodal at node A. Okay, so we're going to have current flowing to the left, up, and to the right, just to frame our equation. So we have VA going to the left, going to ground, so we have VA phasor current, and it's flowing through the capacitor, which the impedance is given as minus J 500 ohms. Okay, so that's the current flowing to the left. So now plus the current flowing up. So the current flowing up is VA going to V out. So it's phasor VA minus phasor V out all over the impedance in that branch, which is the 500 ohm. So it's just 500 ohms. And then going to the left, to the right, I beg your pardon, it's going to the negative input terminal, so IN, and we know that that's 0. Sorry. What I mean is that this is 0, and all of them are equal to 0 because of this, the sum of all of the currents is equal to 0 because of KCL. Okay, so now what do we do? Well, we actually know what VA is because of VP being equal to VN. Okay, and we have a value for VP, and that's right here. So VP is VA, so VP is equal to VA because of the virtual short circuit because of negative feedback, and that is equal to 1 volt with a phase angle of 0 degrees. And then what else can we find out here? Okay, let's convert this minus J500 into Phasor form so that we could do some manipulations. So that's going to be equal to 500 phase angle minus 90 degrees. Okay, so now let's plug in these values into our nodal equation. So we got VA, so that is 1 phase angle 0 degrees over the impedance of 500 phase angle minus 90. So let's do the second term. So we've got VA, we have an expression for VA phase angle 0 degrees, and I'm just going to divide that by 500, and then I'm going to go minus V out, and that was divided by 500, okay, and that's all equal to 0. Okay, so let's go up here, and let's go times 500 to simplify the expression. So then we're going to have 1, and I'm going to bring the 90 upstairs, and it's going to become positive 90, okay, and then the next one is going to be 1 at 0 degrees, and then minus V out, okay, and then 1 at 90 degrees, that's just J, okay, plus 1 at 0 degrees, well, that's just 1, it's a real number, and we'll bring V out to the other side, and that's just V out. So V out is equal to 1 plus J when we put it in standard form, and then very simply we'll just convert it into Phasor form. So J is going to be, the imaginary side is going to be 1, real side is going to be 1, and this is going to be V out, and let's put the little bar on top, and then, well, we know this is a very simple expression, so here, let me just use a different color. So that is going to be 45 degrees with a magnitude of √2, okay? So it's going to be √2 phase angle 45 degrees, and that's what our answer is, √2 phase angle 45 degrees.